address these issues, I started with a couple of models, and I'll present both of those today. One's a population model, focusing on a community of seagrass bed, and another one's a community model focusing on a community of coral reef fish. So the first one's the seagrass model. So the seagrass model in particular was set up for Posidonia oceanica, which is a threatened seagrass species in the Mediterranean. That species is threatened by extreme heat events, which cause die-off, and it's also threatened by poor water quality locally because of sewage outflow and fish farms and other factors which are reducing the water quality in the region. However, it's not known how those two threats interact to affect seagrass. So starting with a simple population model, well, both poor water quality and extreme heat events increase seagrass mortality, so we can model the threats as having an impact on mortality. So this figure just here shows the warming effect in black there, and then the mortality rate was caused by poor water quality in brown. And if there's an additive interaction, and we improve water quality as our local management action, then we expect mortality rate to reduce, and there'd just be the mortality due to the extreme heat events. If there's a synergistic interaction, then improving water quality and reducing mortality rate from the baseline both removes the direct effect of water quality, but it also reduces that interactive effect that poor water quality is having with climate change or warming events. So that actually means mortality rate will end up being lower. Whereas if there's an antagonistic interaction, well, it could go one of two ways. If it's sort of more of a dominance antagonism, such as I described with the coral reefs before and the bleaching and the trawling, then improving water quality reduces mortality rate, but not by that much, because there's still a large effect of the warming. Whereas if it's a mitigated antagonism, then improving water quality can actually increase mortality rate. And this is a bit counterintuitive, as likely to be rare, but there's documented evidence of this happening. So some coral species that are susceptible to bleaching, the bleaching response is also related to light stress. So if water quality is bad, that can actually shade the corals and reduce their susceptibility to bleaching. So in those cases, poor water quality can actually reduce their mortality rate when they're faced with bleaching. So we can stick these estimates into a population model. And so this figure just shows the rate of seagrass density decline, expected rate predicted over the next 100 years, given predictions for climate warming. And the solid line shows not managed, so if we leave water quality as status quo, it's bad what it is currently. And the dashed line shows the managed scenario, so if you improve water quality. And this just shows an additive interaction. So if there's an additive interaction, improved water quality, seagrass density declines slightly slower. If there's a synergistic interaction, then by improving water quality, we reduce the mortality rate by a lot more, and the density decline is much, much slower. So management has a greater effect. Whereas if there's an antagonistic interaction, then improving water quality has very little effect on the mortality rate, and so the seagrass density declines very slowly. So as you can see in this case, the type of interaction, which we don't know at the moment, really determines how effective management on a local scale can be when an ecosystem is threatened by climate change. And so moving on to the community model, which is a model of coral reef fish. In this model, we're interested in two threats that affect coral reef fish. One is overfishing, and the other one is coral reef habitat loss. And this is driven by global warming and bleaching of corals, which eventually causes loss of habitats, which are key for some coral reef fish species. So I wanted to explain the conceptual framework I used to address the community. Say we're interested in predicting, maximising the number of species in that community. And we go out and we measure the vulnerability of each species to climate, so that might be moving from left to right there. Higher on the x-axis means a species more vulnerable to climate change, so it might be a species that's very dependent on coral reef habitat, so it's likely to be at risk of going extinct if you lose that habitat from bleaching. And then on the y-axis is the species vulnerability to fishing. And so each point represents one species and its vulnerability to both fishing and climate. So if the species are randomly distributed like that, and we have moderately high climate impacts and also moderately high fishing pressure, then we can expect to lose 75% of the species. However, species vulnerabilities to the two stresses might not be randomly distributed. They might be negatively correlated. Oh, sorry. So if they're randomly distributed and we reduce fishing pressure, for instance, by creating a marine protected area, then we save about 25% of the species. If species vulnerabilities to two pressures is negatively correlated, that means that species that are not particularly sensitive to climate are sensitive to fishing and vice versa. So if we have both high fishing pressure and large climate impacts, we lose almost all of the species. But managing to reduce fishing pressure saves about half of the species. So in this case, management has a much larger impact. Finally, there might be a positive relationship between their vulnerabilities. So species that are sensitive to climate are also sensitive to fishing. And in that case, if we reduce the fishing pressure, then it actually has very little effect because most of the species are still affected by climate change. And the reason this conceptual framework is useful is that a number of people have now started trying to compile for different communities how they're vulnerable to different sorts of threats. So I borrowed this figure from Nick Graham's work, which was published in 2011. And he looked at, for a large number of coral reef fish species, what their vulnerability was to both fishing and climate. He found this sort of negative relationship. So that means in terms of improving species richness, management on a local scale to reduce fishing pressure can protect a large number of species, even when there's climate change impacts. And the reason for this negative relationship was that species that were sensitive to climate are like a lot of corallivorous fish, like butterfly fish, and they're not particularly important in the fisheries where he was working. Whereas species that were vulnerable to fishing were not as sensitive to habitat loss. So to summarise both the population and community model, well, synergism can cause faster declines, and this is why people are commonly be concerned with them, but they're also an opportunity for management on a local scale to make a difference and have improve ecosystems that are faced with climate change impacts. Whereas if they're antagonisms, then management may not be successful. There's not much management can do when, if managing a local stressor when faced with climate change impacts. So to manage antagonisms, you really need to act on both climate change and the local stressor, or find places where climate change isn't having as large an impact, such as refuges. So this led me to propose a few management recommendations. I've caveated that with all else being equal. This is because when, I guess, deciding on priority actions or sites for management, you also need to consider the cost of those actions and how effective they're likely to be and whether or not they're likely to be actually implemented. But all else being equal, then if there are multiple stresses, these results suggest that you should be acting on those that interact synergistically with climate change. So for instance, back to the Posidonia, and so as well as being threatened by poor water quality, it's also threatened by trawling, which destroys Posidonia habitat. And we might expect that poor water quality interacts synergistically with climate change because physiologically it may increase their susceptibility to being stressed when there's an extreme heat event, whereas trawling will probably interact antagonistically with climate change because seabeds that are susceptible to die-offs after extreme heat events, well, trawling over those is not going to have any additional mortality if the seagrass there is already dead. Another common problem in conservation planning is where to act in space. For instance, where to place marine protected areas or which river system is best to try and improve water quality and to improve water quality to the coast. And so that's a question I'm working on at the moment to incorporate these interactions into spatial prioritisations. And from a research perspective, there really needs to be a greater focus or a more balanced focus on identifying both synergisms and antagonisms. So at the moment, the literature tends to focus on synergisms because I guess they're a bigger story and they imply things will be a lot worse in the future. But antagonisms are just as important, so researchers should be really trying to identify antagonisms and understand the mechanisms that drive antagonistic interactions, because they're really important for informing management of ecosystems. So just to summarise today, I hope I've convinced you that climate change is already having an impact on marine ecosystems today, and that management at a local scale needs to consider interactions of local threats that can be managed with climate change in order to be successful. And before I finish today, I just wanted to mention what I'm doing for my future research. So I'm currently a postdoctoral fellow, and now my research is shifting more towards looking at conservation and food security in the Coral Triangle, specifically working in Indonesia. I'm looking at questions around marine reserve design to benefit both conservation and fisheries, and also looking at the impacts of logging and forestry on coastal reef fisheries. Thank you very much for your attention today.
Before we move on to the questions, we have time for that, I would like to announce a big event for next week. It's actually the Larkin Lecture. We will be hosting the Larkin Lecture here, and we will have as a guest speaker Professor Patricia Masluf from the Cayetano Heredia University in Peru. She will talk about the little brown fish on your pizza and an ecosystem-based view of the world. So please be here next week. It's on Thursday. And now, if anyone has a question, please go ahead. Go ahead.
When you talk about seagrasses, you're talking about the tropical species.
Yeah.
And nothing to do with the eelgrass that we have up here?
No. I guess the general principles would apply to all seagrass, but yeah, the model specifically is targeted at the Mediterranean species.
Another question? Go ahead.
Kristen, really enjoyed your talk. So, you show that the synergisms and antagonists are really important. What if we don't have the research to know what's going on? I mean, and you've got more than one stressor happening in your ecosystem. How do you manage then? Do you have any ideas on that?
I think the safest thing to do is to try and, I guess, target the management towards refuges from climate change. So if there's an antagonistic interaction with climate change, like with a coral reef that's bleaching, then you're unlikely to be able to do anything about the bleaching. So you're better off trying to reduce threats in places where there isn't going to be bleaching. So if you can identify refuges from climate change, such as some areas in the Caribbean where there's cold water upwelling and those reefs are very resistant to bleaching, then that might be a better place to focus on fisheries management or stopping coastal development to improve water quality.
Go ahead.
Just maybe a follow-up question to that, since the antagonisms and synergisms are so important. And you pointed out that Nick Graham work showing some systematic patterns. Is there any other work that looks at sort of systematic patterns or mechanisms that could actually be predicted?
Yes, so there's a fair bit in the lakes literature, I think. So the original paper, they looked at lake phytoplankton and its co-sensitivity to different stresses. Yeah. I think the appealing thing about that concept is it's relatively easy to get the data.